Okay, the next section of this chapter is bond energies. We're going to briefly introduce it. We'll get more into bond energies in later chapters. But the whole idea is that when bond energy is just basically breaking, when we break and form bonds, there's energy involved in that. We refer to talking about, the bond energy or the energy needed to break and form bonds as delta H. And again, we will talk more about delta H when we get into thermodynamics. So when we break bonds, we have to put energy or heat into the compound to break the bond. And likewise, when we form a bond, energy is released. Okay? So when we put energy in, that's endothermic. Putting energy in, heat or energy into something to break bonds. When we release energy, it's exothermic. And energy is released when bonds are formed. So the amount of energy it takes to break bonds or to form bonds is bond energy. So the kind of general trends are the more multiple bonds that are present, the stronger the covalent bond is. So if I compare carbon only bonded to carbon, but I compare it with a single bond versus a double bond versus a triple bond, the more multiplicity there is, the more multiple bonds that are there, the more energy it's going to take to break those bonds because they're stronger bonds. So if you look and you see the carbon triple bond versus carbon double bond versus carbon single bond, it's exponentially higher energy in the triple bond than it is for the single bond. Okay, that's because a triple bond is the shortest of those three and a single bond is the longest. This gets us to part two. The shorter the bond, the stronger it is also. Think about it this way. If I have a ball in my hand and I'm holding it outwards, right? And I'm like, okay, I want you to try to get the ball from me. It's going to be very easy for you to just take that ball out of my hand. But if I'm holding it very close to me, it's going to be much more difficult for you to get that ball out of my hand. I have more strength as something is closer to me to maintain the shared electrons. All right. So the shorter the bond, the more multiplicity, the stronger the bond. The stronger the bond, the more energy or heat that's needed to break those bonds. Bond strength increases as you go up and to the right of the periodic table. So if I'm comparing BRF with BRCl and BRBr, we can see that fluorine is much higher on the periodic table than bromine, and therefore there's going to be a much smaller or shorter bond length. Okay, and you can see that it takes much more energy to break a fluorine-bromine bond than it does a bromine-bromine bond. So these are just average bond energies. You don't ever have to memorize these. You will always be given them on a test question or something like that. If it's a mini quiz and they don't give it to you, it's usually because they expect you just to look it up. Because those are like book problems. So don't worry about that. But on a test, you don't have to memorize any of these, but you do need to understand how to use it. It'll be very important when we get to calculating bond energy, products minus reactants, which we'll get to in a second, and making sure that when you're calculating, you're actually using the correct number based on what you have. So if I had something like this, let me make sure there it is. Okay, for this double bonded oxygen, I have to use this number, but for this double bonded oxygen, or single bonded oxygen, I need to use that number. It's just important to pay attention to those details. So bond energies, we call them average bond energies because it's been experimentally designed and figured out and determined So with many, many, many experiments and reactants. So everything you see on a chart is an average of those double bonded carbons and oxygens or single bonded hydrogens, et cetera, et cetera. It also works best when all reactants and products are in the gaseous state. A little bit trickier when they're not gases. So we talked about bond breaking being exothermic. That's going to give us a positive delta H. I said exothermic, sorry, endothermic. Bond forming is exothermic, which is a negative delta H. All right. So the delta H of the reaction is just simply calculated by adding up all the values from this table of the bonds broken and adding it to all the values from this table with bonds formed. So bond length, we already said, the shorter the bond length, the stronger it is and the more energy it's needed to break that bond. Bond length is simply measured from nuclei to nuclei of two things that are being bonded together. Now, normally we would say, okay, well, here's one thing, here's another, here's their nuclei, and that's the bond length. The problem is these atoms overlap. So really, experimentally, bond length is actually shorter than what we would anticipate. And you don't have to memorize these either. Okay. So this is just your summary of everything I just went through. As bonds get longer, they get weaker. The shorter the bond, the stronger it is. The more multiplicity, the stronger it is. And the stronger something is, the more energy it's going to take to break those bonds.